So students, in the previous class we handled an LPP of less than equal to type of constraints, but in fact we can have the LPPs involving mixed type of constraints, some less than equal to type, some greater than equal to type, and some of equal to type. So here I am taking an example of greater than equal to type of constraints, although the same method that we are going to use can be applied to the mixed constraints. Even some are of less than equal to type, some are of equal to type, and some are of greater than equal to type. Okay, whenever we encounter greater than equal to type of constraints, what we do, we apply big M method to solve the problem. Okay, so here it is an example on big M method. So minimize Z is equal to this, subject to the constraints, these two of greater than equal to type, x1 greater than equal to 0, x2 greater than equal to 0. What is first step? Convert this into standard form. Normally in standard form, the objective function must be of greater than equal to type, so maximization type. So here the given is of minimization type, you just multiply by minus sign. Minimization gets converted into maximization. So this is maximization z dash minus 12x1 minus 20x2. Now what we do in the first constraint, we subtract surplus variable cx6x1 plus 8x2 minus s1, and similarly in the second we subtract surplus variable second 7x1 plus 12x2 minus s2, and since if we find the solution only with the help of these two variables, I get a solution of the type like s1 equal to minus 100, s2 equal to minus 120. The solution will not be feasible one. So that's why what we do, we add some artificial variables to both the constraints, here a1 and here a2. So now this left hand side becomes equal to 100 and 120. All these x1, x2, s1, s2, a1, a2 get equal to 0. And I have already told that the coefficients of slack or surplus variables will be 0 in the objective function, whereas for maximization kind of problem we take minus m coefficient to the artificial variable. So I have minus m a1 minus m a2. This is my standard form. After that I find the initial basic feasible solution by setting all other variables equal to 0 other than these artificial variables. So if I solve those two equations, I get a1 equal to 100, a2 equal to 120. So next step is making the simplex table based on the data available in the standard form. So here CB basic variables are what? A1, A2, their values are 100, 120, and the coefficients are minus m, CJ row minus 12, minus 20, 0, 0, minus m, as usual as explained earlier. Okay, now what is B? B means the values of these variables, that's 100 and 120, and the coefficients of x1, x2, s1, s2, a1, a2 in the whole both the constraints, both the equations. So these are written over here, first row and then second row. Now again we find out ZJ using the same formula as discussed earlier. So it is minus m into 6 plus minus m into 7, so minus 13m. Similarly minus 20m, m minus m, minus m. ZJ minus CJ now, so this is ZJ, subtract this one. So minus minus plus, so minus 13m plus 12, minus 20m plus 20, m 0, 0. So are all these values positive? No. Here we have a negative value and here we have a negative value. So this is the most negative, minus 20 into m. Okay, so the variable corresponding to this will enter into the basis, that is x2 will enter. And how to find out the variable moving out of the basis? Find out minimum ratio. So minimum ratio is nothing but the division of entries or elements under B okay, by the corresponding elements in the entering variable. So 100 divided by 8, 120 divided by 12. Here I have written, so 12.10. So 10 is minimum, so A2 will move out. Okay, this is the decision that we did. Now in the next table, what we do? Again we write C0 as it is. Here instead of A2, X2 is written and corresponding cost is written, that's minus 20. Okay, all these right hand side values are changed now. Okay, what was the, this was the, you know, what was the, this one was the key row. So key element was 12, divide all this by key elements, so 120 divided by 12, 7 divided by 12 and so on. We can see here 10, 7 by 12, 1, this minus 1 by 12 and 0. Okay, and using the same formula, that old row minus I have done somewhere, it is, this is old row. Okay, old row elements you can see here 106, 8 minus 1, this. So old row elements 106, 8 minus 1, 0, 1 and minus element in front of the key element in the same row, that is 8. So 8 multiplied by the new key row element. So here we can apply 10 into 8. 80, 7 by 12 into 8 and 1 into 8, 0 into minus 8 upon 12. So I have written all these values here and then subtracted. After subtraction I get 12, 4 by 3, 0, minus 1 and 2 by 3 and 1. So I put these values now here. So this is my second row, new row. Okay, we can see here that I have not computed the values for A2. There is no need. Please remember, whenever some artificial variable is moving out, so do not perform the calculations corresponding to that variable, because we are never interested in artificial variables in our further calculations. These were only added for the sake of initial solution. So once these are out, there is no need to uh, do the calculation for them, so that the scope of further returning to the basis is 0, no scope. Okay, so so A2, for A2 no calculations are done. Okay, now again we find ZJ. The ZJ values are computed as usual. This is for x1 and this is for x2, this is for s1 and this is for s2, minus 2m upon 3 plus 5 upon 3 and minus m is the value for a1. Okay, so this arrow is simply denoted to represent that this is for A1, because these are quite closer together, so one may get confused that okay, this bracket value is minus m. So it's not minus m value for A1. Okay, then we do ZJ minus CJ, we get these values. Okay, this is again negative, or and this is also negative, is positive. So among these two, this is most negative. So variable corresponding to this x1 will enter into the basis, and the minimum ratio we can find like this 20 divided by 4 by 3, 10 divided by 7 by 2. So we get this 15 is lesser than 17.5. So A1 will move out now. Okay, doing the same kind of calculations, we get a new table. So this is x1, x2 are here, b values are these are all other values, computing again ZJ like this and ZJ minus CJ like this. So using the same procedure, all these values now positive, so all ZJ minus CJ. Your solution is optimal, hence the solution is x1 is equal to 15 and x2 is equal to 5 by 4. Therefore, this minimum value is the minus of maximum z dash, that is what I get from here, just multiplying with this, minus 12 into 15 plus minus 20 into 5 by 4, whatever I am getting. So put minus sign before that and it is 205. And these lines like this. So the material or the calculations done below them are just for reference. These are rough calculations. So right side, well, here also these are all rough calculations that I have done. You can refer to these for finding the values which are available in these tables. Okay, so above this it is okay, but below this curved line, lines, this is rough work. Okay, so this is how we eliminated the artificial variables from our simplex tables, and finally we got a solution, okay, which is free from artificial variables, and hence this is optimal also. So this is my optimal solution. This is how we work with bigger method. Okay, suppose instead of x1 it would have been a1 is equal to 15. So in that case, what is happening? Artificial variable is is present at positive level, that is 15. If the value is like this, okay, then we will conclude that this problem will have no feasible solution or infeasible solution. So please note that if any artificial variable appears at the positive level in the final optimal table, then we say that this problem has no feasible solution. But in case here, in this case, we don't have any artificial variables appearing in the final table, so we have obtained optimal solution, and this is how we write it. So what is new in this? Every time what you have to do whenever you have to make the standard form, you first start with the maximization kind of objective function. Just minimize z is equal to minus of maximize z dash, or maximize z dash is equal to minus of minimum z. So all the values will be multiplied by right hand side values will be multiplied minus sign, and at the end again you convert to the original objective function and just simply multiply by minus sign to the last value. Okay, this is how this bigger method works. I hope you have understood. In case of any problems, you can discuss in the class. Okay, thank you.